All right, we are picking up on 4.5, and this is a continuation of compounding. This is continuous, so I don't know why that happened. So continuous compounding. And the idea here is that if we take the compound interest formula, there's the compound interest formula, and let's suppose we're going to double our investment. So let's say R is equal to 1. So if we double our investment, our growth factor is basically 2, right? So remember, you have 1 and then you add on your growth factor, your interest rate. So if we're doubling, our multiplier is 2, so 1 plus 1. So when we double, we're increasing by 100%. If we compound that once, right? If we compound it annually, oops, I want to write that down there. So compounded annually, we get a growth factor, or a B value, of 2, right? Because we do 1 plus 1 over 1 raised to the 1. Because if we're compounding annually, n equals 1. And this turns out to be 2. All right, if we compound, let's say, semi-annually, where n equals 2, well, now we have 1 plus 1 over 2 raised to the 2. So let's figure out what that is. So that's 1 plus 1/2, and then it is raised to 2. And so we get 2.25. Okay, so how about if we do this monthly? N equals 12. Well, we'd have 1 plus 1 over 12 raised to the 12. So if I do that on my calculator, I end up with this long decimal of 2.613035529 and so on. Okay. And what's happening here? The B value is getting larger and larger because the more times we compound something in a year, the more interest that is gaining interest, right? It just kind of keeps gaining interest and interest and interest. So if we increase this to daily, I'm going to do that calculation to see what we end up with. And we get 2.71456748, so on. Okay. And again, the B value is getting larger and larger. But we're talking about compounding continuously. So not just every day, not just every hour. Right? I can keep going here. We can keep increasing n to be hourly, or every second it's compounded. But we want to keep going and going and going so that it's compounded continuously. And that's the idea of a limit, remember. So a limit is a value that a function approaches. So what I could talk about here is I could talk about what we're doing in this formula, which we're taking this part of the formula and we're changing the n value, right? That's all we're doing here. So if we look at the limit as n approaches infinity, so as we compound an infinite amount of times in a year, what happens? Well, we can't just plug in infinity, right? So we have to look at the limit as n approaches infinity. That's the idea of a limit, right? So as n gets larger and larger and larger, what happens to this b value? Does it go to infinity? Well, if we notice, it started at 2 and then it kind of increased, but the rate at which it's increasing is slowing down. And so that's actually going to lead us to a certain value. And so if we look at the book is talking about this number e, which is what this approaches. So right now we're at 2.71456-ish, and e is approximately 2.71828, and that goes on forever. It's an irrational number. So as the compounding continues and continues, we get to this e number. And so now we kind of just define that to be a value. It's a value. It's approximately 2.71828. And there's a button for that on your calculator as well. So for continuous growth, or continuous compounded continuously, our formula is Q equals A times e to the kt. And k is the continuous growth rate. So the continuous growth rate is just the decimal part of the percentage. You do not have to add 1 or anything to it. And if it's growth, if it's continuous growth, it's a positive value. If it's continuous decay, it's a negative value, and so on. So, for example, give the continuous growth rate for each of the following functions and graph each function. No, let's not do that. Example 2. Population increases from 7.3 million at a continuous rate of 2.2% per year. Write a formula for the population and estimate graphically when the population reaches 10 million. So let's take a look at how we would set that up. So it increases from 7.3 million. So if we keep our units in millions, we could just say our starting value is 7.3, P for population. Remember, you can just change all of these things. But this is a number, is a value, you can't change that. That's not a variable. So it's important to remember that E is not a variable, it's a number, much like pi is a number. And then the continuous rate of 2.2%, so I should actually write down in our notes what we're doing here. We're starting at 7.3 million people and then increasing by 2.2% continuously. So the 2.2% increase continuously, I convert that to a decimal. So that's 0.022 and then t. That would be our formula. Okay? And we could just plug this in and put that into y1 and put 10 into y2 and find the intersection point. Okay? Example 3, caffeine leaves the body at a continuous rate of 17% per hour. How much caffeine is left in the body 8 hours after drinking a cup of coffee containing 100 milligrams of caffeine? So that's a good example to work out. So if we have 100 milligrams of caffeine, decreases 17% continuously. Now notice it does say per hour, but it's continuous. So per hour is just telling us what our T is measured in. Right? In the last example, the population was per year, so T was being measured in years. This one, it's per hour, so T is being measured in hours. So 100 milligrams of caffeine decreases 17% continuously after, so I'll just add that in there, per hour. So after 8 hours, how much is left? So the quantity would be equal to 100 times E, and then a decrease of 17% for continuous means just put negative 0.17. And so we're just going to plug in 8 and figure out what that comes out to be. So I will do that in my calculator, and hopefully you guys are checking that as well to make sure I don't make any mistakes. So let's see. E raised to that times 100. So it looks like I'm ending up with about 25.67 milligrams, which would be the answer there, if I did everything correctly, which I think so. All right, seems like a reasonable answer. Good. So the next thing the book goes into, it's out of the way, is again that idea of how we relate these when we do this versus that. So if you notice, to relate the B value, the growth factor, to the continuous growth rate, these two things are the same. So B is equal to E to the K. So that is going to be useful if we're looking for growth factors or nominal interest rates or effective interest rates or whatever that may be. We can find the B value that way. So we just have to take E and raise it to the K, continuous growth rate. So book goes into the example that I was showing there earlier, right? As the n increases and gets larger and larger and larger, approaches infinity, the number approaches that value that we call E. And there's our formula. and so on. So that's about it for notes. And you guys have a problem set 4.5 that you can work on. And yeah, if you have any questions, you can send me an email. And that's about it. I will see you guys next time. All right.